Hi everyone. So we ended class yesterday talking about, we had been talking about a vertical stretch and shrink to a parent graph. And we just started to look at a different type of transformation. So I asked us to graph y equals x squared, y equals 2x quantity squared, and y equals 1/2 x squared on your calculator or Desmos. I actually did it on Desmos. And here's what I have. So the red graph is actually y equals x squared, and the purple graph is y equals 2x quantity squared. Now what I'm hoping you notice is that it did get narrower than the red graph, but let's look at what actually changed in the graph. So if I look at my tables here, the red graph is the parent, and let's look at the tables. You might notice that all of the x values actually changed, okay? All of the x values actually changed. And here, if you look at the points, at the point 2, 4 became 1, 4. The point negative 2, 4 became negative 1, 4. So all of the x values actually got cut in half. Then, if you look at y equals 1/2 x squared, and you consider those points, it looks like all of the y points got actually multiplied by 2. It goes from 2, 4 to 4, 4, or negative 2, 4 to negative 4, 4. So this is an interesting thing that happens. When you are dealing with something inside the function, it actually provides us with a horizontal stretch or shrink, which means that it could also have a vertical stretch or shrink. So let's take a look. If you have a function in the form y equals f at cx, the x values are being directly affected, and the scale change will result in a horizontal stretch or shrink. Sorry, I can't speak today. So if c is greater than 1, which is what we saw with y equals 2x squared, it was a horizontal shrink, which means that a vertical stretch will happen in most cases. And if c was less than 1 but greater than 0, it gave us a horizontal stretch, which means a vertical shrink in most cases. So I always like to think of it as it's not obvious when it's on the inside that it's going to give me a shrink. Like 2, you'd love to think it's making it bigger, but it's actually dividing it in half. So I call these not obvious, the not obvious ones. All right, let's see how that's going to affect our rule. So here's our example. Let's first state whether they undergo a horizontal stretch or shrink. Okay, so the 3, the c is inside the function. This function is the square root. It's on the inside, so it's going to change x's, but this would then be a horizontal shrink by a factor of 1/3. Okay, this one, absolute value is the parent. This is going to be a horizontal stretch by a factor of 4. Because remember, when we did y equals 2x, we cut it in half. And when we did 1/2 x, we multiplied by 2. So it's actually the reciprocal that when it's on the inside of the function. All right, so y equals f at 2x. This would be a horizontal shrink of a half. And then f at 0.5x would be a horizontal stretch by a factor of 2. Mr. Hamilton likes to say it's counterintuitive. Ms. Cortez likes to say it's like the not obvious answer, but you're really taking the reciprocal of your x values. All right, so let's talk about the rule, because everything we do for these horizontal stretches, I'd like you to consider the rule that's happening and what's changing, the x's or the y's. So remember, inside the function changes x, outside the function changes y. So if the function is the square root function, then the rule in this case would be 1/3 x, comma y. Just like in this, y equals 1/4 x, my rule would then be 4x, comma y. All right, so general functions, then this would be 1/2 x comma y, and the next one would be 2x comma y. So we're multiplying the x values by the reciprocal of whatever your c is, okay? All right, so let's put this all together. So for each function, it says write the equation of the parent, the rule, and then graph the function. Okay, so let's look at it. Our parent graph we know is y equals the absolute value of x, so we should be like considering that this really looks like a v, right? I'm gonna make sure I'm on the right page with you guys. I am not. There it is. Okay, just want to make sure I have everything in front of me. Our scale change would be it would be a horizontal stretch of 3. Okay, and my rule would be 3x y plus 4, because that 4 is still moving the graph up 4. Okay, my vertex in this case would be 0, 4. Okay, all right, so let's graph that. I think I have that on the next page. So how do we graph it? We're going to make our table of values. So x, y, -2, -1, 0, 1, 2, and 2, 1, 0, 1, 4. My rule, I'm going to state my rule. So we said that our rule was 3x, y plus 4. I'm going to multiply all of my x's by 3. So that's going to give me -6, -3, 0, 3, and 6. And I'm going to add 4 to all my y's. So 6, 5, 4, 5, 6. All right, so 1, 2, 3, 4, 5. One more, -6, 6 would be up here. -3, 1, 2, 3, 5 would be right here. 0, 4, 1, 2, 3, 4, 3, 5, 1, 2, 3, and then 6, right there. And so it's a very wide graph. Okay, so let's think about the domain and the range. So my domain, again, it's absolute value, so it doesn't change even when we translate the graph. It's going to be -infinity to infinity, but my range always is related to the y-coordinate of the vertex. The y-coordinate of the vertex is 0, 4, so it would be hard bracket 4, infinity. Okay. All right, I want you to try the next one and bring that one to class. And I also would like you to try, let's look at these next set of examples. So we'll do a few together, and then you'll bring them to class tomorrow. All right, so if we have a parent function and we want to write an equation from the given information, we just need to make sure we know which part goes inside, which part goes outside, which affects x, which affects y. So in this case, we have the absolute value of x. It's going up 7, which means it's on the y, and left 3, which it's on the x. So if it's going to the left 3, we know that our function has to be the opposite sign inside. So x plus 3. And up 7 would be plus 7. Okay. The next one, we've got y equals x squared. We're going to actually add to this. It should say reflects over x-axis. And right 9. Okay. So we know that the negative in front of the function would make it reflect. So that would be negative. And then it's going to the right, which is left, right, which affects my x. So it's on the inside. If it's going to the right 9, we need to do x minus 9 squared. Okay. All right, I want you guys to try 3 and 4. I want the reflection to be over the x-axis. And we will go over the remaining translations tomorrow. All right, have a great day. Yes, I think that.